Hi everybody, today we're going to be doing section 9 talking about machine learning. So we're going to start off with problem number 1 talking about the naive Bayes. So a naive Bayes classifier is just a particular form of Bayes net pictured here on your worksheet. So we have a variable that we're trying to predict. In this case, it's variable y. And then we also have down here the features. So we can have a large number of features, and these will all be pointing down as arrows from the predicted output y. So here, in this case, we only have two features, and those are A and B. So the idea here is that we're going to get training data, that's this table here, that has samples from this classifier. So we have, in this particular example, we have A has value 1, B has value 1, and the output y has value 1. We're going to get all these examples, and we're going to use these examples to learn the probability tables for our classifier, and then at test time, we're going to take new values of A and B, and we're going to predict the values of y from the A and the B. So what we're first going to do is we need to figure out what are the probability estimates for this classifier for this Bayes net. We're going to do that from our training data. So this is part 1, and we're going to use maximum likelihood to make our estimates. So in order to get the maximum likelihood estimate from our samples, we're going to use counts from these samples. So this is similar to when we did sampling. Basically what we want to do, say we're trying to find P of A given y. P of A given y is going to be equal to the count of a particular A and y divided by the count of y. And this looks similar to our probability rules of the conditional probability. This looks like P of A comma y over probability of y. But we're going to use the empirical counts in order to estimate this, rather than any sort of actual probabilities. Okay, so let's take a look at our first table. So in this case, we're not conditioning on anything. So what we're going to do is we're going to count the number of times y is equal to 0. So in here we have 1, 2, 3, 4, 5, 6, y 0. And count the number of times y equals 1, that's 4. So our counts are 6 and 4. And our total count that we're going to normalize over is 10. So the probabilities that we're going to get are 6 over 10 and 4 over 10. Now we're going to do the probability of A given y. And so we're going to similarly use counts from the same table here, but now we're going to look at counts where A and y are equal to the values in the table. So we're going to start off with A equals 0 and y equals 0. And we're going to look in our table up here, and we're going to see that there is only one place where they're both 0. Then we're going to go and say A equals 1, y equals 0. We're going to look in our table. A equals 1, y equals 0 happens there, there, and there, as well as there and there. So that's 5 counts there. Okay, then 0 and 1. In our table, we have one instance of that. And then finally, for 1 and 1, we have 3 of those. And so now, here, this is the distribution that we're going to normalize, because this is a given y, and we want to normalize over y's. So here, these are all the instances where y equals 0. We're going to say this is going to be a total count of 6 for y equals 0. So this is going to be 1 sixth. This is going to be 5 sixth. Then over here, we're going to do for the case where y equals 1. And this is going to be 1 over 4. And this is going to be 3 over 4. So hopefully now you've got the rough idea. So let's kind of go fairly quickly through this last part. So we count where b equals 0 and y equals 0. And there's going to be one of those. Sorry, there's two of those. All right, and then there's 1, 0 is 4 of those. Then we have 1 and 3. So these are our counts. And now we're just going to normalize. So this is 2 over 6, because again we added 2 and 4 to get 6. So that's 1/3. Then we have 2/3 here. This is going to be, our sum is 1 and 3 is 4, so 1/4 and 3/4. All right. So now what we've done is we've used this training data in order to calculate our parameters, which in this case are probabilities for the Bayes net. So we want to figure out now, what if we saw a new data point that wasn't in our training data? How are we going to estimate? What we want here is the probability of y given a equals 1 and b equals 1. Sorry, b equals 1. And so once we have this probability, then we can use this to assign a label to y, and we're just going to use the most likely label. So how do we calculate probability of y given a and b equals 1? Well, all we need to do is we need to do the probability, the joint y equals 1, a equals 1, and b equals 1. And then similarly, we do the probability that y equals 0, a equals 1, and b equals 1. Okay, so looking at our Bayes net, what is this probability? Well, we're just going to have, that's the probability of y times the probability of a given y times the probability of b given y. And we look these up on our table. And what do we see? Well, this is probability of y equals 1. That's 4/10. We could also write 2/5, of course, but I'm just going to keep it in the 4/10. Okay, probability a equals y for 1 and 1. That's 3/4. Okay, and then b equals y also for 1, 1. That's 3/4 again. That's going to be end up being 9 over 40. 9 over 40. Okay, so we're going to do the same thing for the case where y equals 0. So here, probability of y, that's 6 out of 10, multiplied by probability of a given y. So now we're going to say y is 0, a is 1, that's 5 out of 6. And then b equals 1, given that y equals 0, well, that is 2/3. We multiply all of those together, and we end up with 1/3. All right, so now we have two probabilities. This is the joint probabilities. So we could go ahead and normalize, but it turns out in order to make the decision, we don't need to normalize because this is just going to be kind of multiplying by a constant. So we can look at these two, and we're going to decide which one is greater, 9 over 40 or 1/3. And 9 over 40 is going to be less than 1/3. So we're going to choose 1/3. This is the greater one. And our label is going to be y equals 0. All right. For the final part of this section, it's talking about Laplace smoothing. So the idea of Laplace smoothing is that sometimes if we just do the counts directly, we might end up in bad situations. And in particular, a bad situation we might encounter is, what if a count is 0? So if a count is 0, we're going to estimate the probability as a count divided by some number. And if this is 0, we end up with a 0 probability. And 0 probabilities are generally just a bad thing to have. So now any time we see a point that happens to have this particular feature, we're going to say that that label has 0. So we estimated these from a finite amount of data, and so saying it's actually 0 and not 0.00001 is generally a bad idea. So we would rather have a little bit of a smoother estimate. And the way we do that is we're going to add kind of pseudo counts. So above we had some counts, and I'm just going to copy those down. So this is for the probability distribution of A given Y. So for here 0, 0, we had 1, 1, 0, we had 5, and we had 1 and 3 for the other two probabilities, or sorry, for the other two counts. So how are we going to do Laplace smoothing? Well, we'll just add 2. In this case, k is 2 to each of the counts. So we end up with 3, 7, 3, and 5. So now these are our, I'm going to call them count prime. This is a kind of smooth counts. And so now we're going to use these counts instead to do our probability estimates. We're going to go in the same way. We're going to normalize. So here, we're normalizing over these two. This will be 3 over 10. This will be 7 over 10. Okay, this will be 3 over 5. And this will be, sorry, 3 over 8. I'm going to add. And this will be 5 over 8. And that completes problem 1. All right, now let's move on to the second problem, which is on the Perceptron algorithm. So for this problem, again, we're going to end up with features, and we're going to be trying to predict some output based on those features. So in this case, our features are A and B, and those represent the scores that 2 critics gave for a movie script that we created. And our output is going to be this profit variable, and that is whether or not our movie is going to be profitable. And so what we're trying to do is we're trying to, based on the critic scores, decide, do we think our movie is going to be profitable? So we're given this training data, and we're going to use that to learn a classifier, and then later on, we're going to want to apply this to new movies and try to guess whether they're going to be profitable before we actually make them. So let's start out by trying to look at the data we have now. And so we're going to plot all these examples. This is part 1. So we're going to look at each example, and we're going to put it on this plot over here. So start off, our first movie has scores of 1 and 1. So if we look at our plot over here, that'll be right here. And we saw that it's not profitable. So I'm going to draw a little negative down here. So that's for our first point. Now let's look at our second point. We got 3 and 2 are our scores, and it was profitable. So 3, 2, I'm going to draw a plus. Similarly, 2, 4 is a plus, and 3, 4 is a plus. And then finally, 2, 3 is a minus. So the question here is asking, is this data linearly separable? Why do we care about linear separability? Well, it turns out that our Perceptron algorithm is designed to draw a line between our data, and if you can't draw a line between it with the features we're given, then we won't actually be able to use Perceptron algorithm to get a perfect classifier on our training data. Okay, well, let's look at our plot here. It turns out for these 5 points, we could draw a line roughly through here. It should be a straight line, of course, but it's hard to draw. And we can see all the negatives are on one side of the line and all the positives on the other side of the line. So this means the data is linearly separable, and our Perceptron algorithm will eventually be able to find that line. Okay, so let's look at part 2. So this is actually going through and working on the Perceptron algorithm. Before we actually go through the details of the algorithm, though, I want to point out one thing, and this is talking about a bias. So our kind of generic thing we're going to score for a Perceptron is we're going to have a vector of W, and we're going to do a dot product W with a set of features of X. So this is a vector, features of X would be A and B, and then W is a vector. I'm going to say W1, W2. And so if we do the dot product, this is written as W transpose F. And so we would do W transpose F, and we'd compare that to 0. We'd say greater than or equal to 0. So this is how we make our classification decision. So if we were kind of to draw over here, what can this actually do? This is going to draw lines, but all the lines that we can draw are going to be through the origin. So the problem here is that is a very constrained set of lines. What we'd really like to be able to do is draw lines like this line here that's not going through the origin. So how can we adjust our decision to do that? Well, one way would be to write W transpose F plus B is greater than or equal to 0, with this as our new decision rule. But that's a little bit annoying because we have this B that we have to kind of treat separately. So a nice trick that we can use is we can append a special feature to the end of our feature vector that always has a value of 1. And then to our weight vector, we append a B. So we're kind of extending our vectors. So now what happens when we take this dot product is we already have a term that adds in a B times 1, which is just adding plus B. And so this is a convenient way to add in the bias without having to do anything separate, special for it, because now we can just do our dot product as if it was normal with this one extra feature. Okay. So actually, for this particular problem, we're going to put the B at the beginning, but that's just kind of a minor detail, so I'm going to put it up here, B and 1. All right, so now let's start working through the perceptron algorithm. So let's take a look at our first step. Each step is going to go through one of the data points and update the weights that we have. And we're given initially this set of weights here. So you can kind of start with a random value here, or just all zeros. Here we're going to start with -1, 0, 0 as a reasonable starting point for our weight vector. Okay. So now, how do we use this weight vector to classify a point? Well, what we're going to do is we're going to take a dot product of this weight vector with the feature vector. So the feature vector for point 1, we're going to start with the bias term, so I'm going to put that first. So bias term is always 1. Then we have A is 1, and B is 1. So I'm going to write up here. This is A, this is B, and this is the bias. Okay. So we're going to do a dot product. We're going to say -1 times 1, 0 times 1, and 1 times 0. And of course, that ends up being -1. So what we're doing is we're trying to figure out what is the answer that our current set of weights would give on this point. And of course, it gets a -1, so that's saying that it's not going to be profitable. So if we have a negative score that's less than 0, then we're going to classify that point as a negative. We look up at our profitability column here, and we see that these match. We predicted a negative, and the actual answer is negative. And so this is a correct classification. And for Perceptron algorithm, when we have a correct classification, we're not going to change the weight vector. And so we're just going to write here, the weight vector is going to be the exact same, -1, 0, 0. Okay, so that's the step of the perceptron algorithm. We saw what the classification would be, and then in this case, we didn't have to make an adjustment at all. All right, so now for step 2, we'll move on to the second point. This is 3, 2 plus. So what is our feature vector? Well, we have the bias is 1, then A is 3, and B is 2. And so we're going to do the dot product of this vector here with the weight vector. So what's going to happen is we get 1 times -1. We're going to write -1 times 1 plus 0 times 3 plus 0 times 2. And of course, this is just negative 1. So again, the prediction that we made for this point, which is a different point, is negative 1. That's saying that we're predicting it's not going to be profitable. And we're going to compare that against the actual probability. Well, here, the actual probability is a plus. So the score does not match the actual output. And so this is not correct. So when our point is incorrect, when our prediction is incorrect for a point, now we're going to make an update of our weights. We only make updates when we have the wrong answer. And the update we're going to make is we're going to take W, and we're going to do W plus Y star times the feature vector. Okay, so Y star here is the actual label that we got. In this case, we're going to say it's plus 1 because our label was plus. And if a minus, we're doing a minus, it would be a minus 1. So basically what's going to happen here, we have a weight vector, and if we got it wrong, we're going to add F, where F is our feature vector, to the weight vector. So in this case, our Y star is indeed a plus 1. So let's go ahead and do that. So we have negative 1, 0, 0, plus 1, 3, 2. So negative 1 plus 1 is 0. 0 plus 3 is 3. 0 plus 2 is 2. So now this is our new weight vector after updating on this incorrectly classified point. Okay, so now let's move on to the next point. So here we're going to do the same thing again. We're going to take a dot product, this time with our new updated weight vector, and we're going to have to figure out what our features are. So let's see, this is number 3. Bias is always 1. Then we have a 2 and a 4. This aligns here. Okay. So 1 times 0 plus 2 times 3 plus 4 times 2. Okay, let's see. So that's 8 plus 6, and that is 14. Sorry, that's equals 14. All right. So now this is greater than 0, so we're going to predict positive for this point. And, well, it turns out our actual label is also positive. And so we got this correct. Yes. And so since we got it correct, we don't have to do any updates. And so we'll kind of copy our same weight vector down. 0, 3, 2. And we'll go on to the next point. I'm going to erase some of these feature vectors because they're getting a little bit crowded. All right. So now what's our feature vector for number 4? It's going to be a 1, 3, 4. Let's do the dot product. 1 times 0 plus 3 times 3 plus 2 times 4. Okay. So what is this? 3 times 3 is 9 plus 8. That's going to be 17. Okay. The thing we care about here is that the score is positive and our label is positive, and so we got it correct. So we write yes here. And we can move on to our next point without changing our weight vector. So we 0, 3, 2 again. All right, and now we're at our last point. What's the features? Well, it's 1, 2, 3. I'm going to put a bracket here. Okay, so we've got 0 times 1 plus 3 times 2 plus 2 times 3, and that is 12. Okay, so here, now we can see this value is positive, but if we look back up at our actual table, we wanted to get a negative here. So this is a mismatch. So what we're going to do is we're going to have to go back and update our weight vector. And how are we going to do that? Sorry, I should actually keep that here. We said it was 1, 2, 3. Okay, so we're going to update our weight vector with this. And so we have our weight vector plus our current weight vector plus y star here is now -1 because we have a negative profit. And then we're going to subtract the feature. So we're going to do our final weight is 0 minus 1, -1, 3 minus 2, +1, and 2 minus 3, -1. Okay, so what we've done here is we've updated our weight vector based on this point by subtracting because it had the actual label was negative. And now we're done with this Perceptron algorithm. We've run through all 5 points and we've updated our weights each time. In actuality, we would probably continue doing this through multiple passes of the data, but here we just went through once. All right, and so our final weight vector is -1, 1, -1. So now we can ask, if this is our weight vector that we learned, has this weight vector learned to separate the data completely? Have we learned kind of this line here that we wanted to learn that goes in between the pluses and the minuses exactly? And so the way we can do this is we're going to go back through all of our points and we're going to see what the classification is. Okay, so for point number 1, we had 1, 1, 1 was our feature vector, and we're going to do the dot product. So we have -1 times 1 plus 1 times 1 plus -1 times 1. Okay, so we have 2 negatives and 1 positive, so we're going to get a -1 here. Okay, and the thing we wanted to get was a negative, and so this is good. We're going to keep on going through and see if all of them are the correct classification. Okay, so our next point is 1, 3, 2. Okay, so we're going to take a dot product with a weight vector. So we have -1 times 1 plus 3 times 1 plus -1 times 2. Let's see, what does that turn out to be? Well, it's a 3 minus 2 minus 1. That's a 0. So this is actually kind of a special case. What do we do if it's neither greater than or less than 0? What if it's actually equal to 0? And so generally what we're going to do is we're just going to tie break by saying we're going to label things, or we're going to call things that have a 0 a positive label. So remember when we had our rule, we said W transpose the features greater than equal to 0. So here we have the equal to. We're going to say if it's equal, it's going to be a positive label. So in this case, we wanted a positive label, and we're good. All right, so far so good. Let's now look at the third point. This is 1, 2, 4. Let's do our dot product. -1 times 1 plus 2 times 1 minus 4 times 1. Okay, so let's see, we've got 2 minus 5, that's a -3. So our prediction here is now a negative. But we look up above, and we actually wanted to get a positive. So what's happened here now is we made an incorrect decision, so we know that we have not actually correctly separated the data. So we could keep on going through all the rest of these, but we already know the answer now is no, because we've already gotten an incorrect decision. So to save time, I'm not going to go through the rest. All right. Finally, we're going to look at some kind of different scenarios and see, are our features going to be powerful enough to handle these scenarios? So the first question is asking us, if the total of scores is more than 8, then we know the movie is going to be profitable, and otherwise it won't be. So what this is saying is that score A plus score B is greater than 8. So this is our decision rule that we'd like to have ideally. So the question is, can we do this with a perceptron using just these two features? And the answer is yes. Why is it yes? Well, because this is a linear rule. We have 1 times A plus 1 times B, and this can be handled by our bias term, the 8 here. You can also see this if we were to draw the coordinate system. So if we have the line A plus B is greater than 8, what that's going to look like is it intersects here at 8 and here at 8. And so everything above this line is greater than 8. And so you can see this is a line, so that means our perceptron is able to classify it. Okay. So in this case, it asks us to circle the ones that we can classify perfectly. So we're going to circle A. Okay. So the next question is saying, our movie is profitable if and only if each reviewer gives either a score of 2 or a score of 3. So what does this look like when we draw it out? So say we have 1, 2, 3, 4, and 1, 2, 3, 4. Okay, so that means if it's 2 or 3 for both reviewers. So that would be like here, 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 or here. These are our positive labels, and everything else is going to be negative. So these are negative. And the question is, can we use a perceptron here? Well, is it linear? No, there's no line that we can draw in order to perfectly separate the pluses from the minuses. If we were to draw this line here, for example, and say that this is the positive side and this is the negative side, well, we get these up here right for the negatives, but we still have all these minuses around here that are wrong. And so there's no line you can draw that will perfectly classify these points, and so I'm going to draw an X here. This is not possible. All right. Finally, it asks us, in this last scenario, our movie is profitable if and only if both reviewers agree. So what does this look like when we draw it out? Well, if both reviewers agree, that's saying like 1, 1 is positive, 2, 2 is positive, 3, 3 is positive, and 4, 4 is positive. And it's negative in all other cases. So is there a line now that can separate the pluses from the minuses? Again, we cannot do this. So the best we could do is draw a line perhaps like right here, but still that gets all of these answers up here wrong. And so this one is not possible because it's not linearly separable. All right, and that is now it for problem number 2. Our final problem today is on maximum likelihood. Maximum likelihood is a general method for choosing a set of parameters for a parameterized probability distribution based on data. So the idea is we have some probability function that has some set of parameters that determines the probability, and we have a set of data that we want to fit. And what we're going to do is we're going to choose the parameters such that it maximizes the probability of the data that we've seen. So we want to choose a parameter that makes the data we've seen most likely. So before we actually get into this particular problem, which is deriving the maximum likelihood for the geometric distribution, I'd also like to point out that problem number 1 was also using maximum likelihood. And so this was like with the counts that we talked about. So if you actually want to see the derivation for that, you can look on homework 9 electronic, and that will show you how you derive this. And what this kind of gave us was the fact that we could use the counts to create the distributions for our naive Bayes. But in general, we want to be able to do this for kind of any arbitrary distribution, not just a naive Bayes. And so the maximum likelihood is the more general method we can use to derive for any probability distribution that uses parameters. How do we determine from our samples what good parameters are? All right, so let's look at this particular problem in the geometric distribution. So we're trying to find the set of parameters for this distribution. Here, the parameter is p. There's only a single parameter. And so we're trying to find the best value of p, given that we have this data that was generated from the distribution. So you can think of, there are lots of different forms of this function, and we're trying to find the particular one, the particular p, that makes it most likely to output these values. Okay, so this is the probability of a single point, probability of a single point x being equal to k. So if we have a whole set of points, a whole data set, what we're going to do is we need to know the probability of the entire data set. And in general, we're assuming independent samples, and so the product will be how we go from the individual probabilities to the entire data set probability. So I'm going to say the likelihood here is equal to the product over I of P of x equals xi. And of course, we can write this out because we know we're kind of assuming this particular probability distribution was used, this parameterized distribution. So we know that this is equal to p times, a product of p of 1 minus p raised to the k minus 1. Here I'm going to put an I, actually, and we're going to put xi there. So the whole likelihood is now the product of this value, which comes from our probability distribution. And this is our model. We're kind of assuming this particular distribution. So this right here is kind of the probability of the whole likelihood of the data. So there's kind of two ways you can go about these problems. When we have a fairly small set of data here, what we could do is we could go ahead and plug in all of our x1, x2 right away. But I'm actually going to do it slightly differently. I'm going to do the more general case of for any arbitrary set of xi's, and then at the very end we'll plug in the x's that we have. And the reason that I'm doing it this way is that this works out nicely because I'm going to get a general formula that we can use any arbitrary set of x's to choose the best p. Of course, on the test it might be easier to do the other way, but it's kind of just a trade-off. It's a personal option for you. Okay, so we have this likelihood here of the entire data set, and our goal is to maximize this likelihood with respect to p. So before we actually start doing the maximization, it's often easier to turn this into a log likelihood. And the reason for that is we have lots of products in this probability here, and when we do a log, things turn into sums. So if you remember our log rules, log of A times B is equal to log of A plus log of B. So what happens if we take the log likelihood of this term here? Well, our product, the outer product, is going to turn into a sum over I. Then we're going to have log of P. Then we're going to have plus the other rule we have with logs is if we have an exponent, we can bring it down in front of the log. So we have k minus 1, sorry, I should say xi minus 1 times log of 1 minus p. So all I did here was I took the log of this expression and I used our log rules to split it out. So here, log p, 1 minus p, and then we move this exponent down in front of the log. Okay, so our goal, now that we've kind of turned it into a log likelihood, which is just for convenience really, we want to find the maximum. So I guess why are we able to do this log is because in general, a log is a monotonic function, and the thing that maximizes the log is always going to be the same as the thing that maximizes the original probability. So anything that makes a log higher is also going to make a probability, the original probability, higher. So we want to find p that maximizes this. Well, if you remember from calculus, a generally good way to find a maximum is to take a derivative and set it equal to 0. So let's take the derivative of this term here. Okay, so we're still going to have the sum over I. Then we're going to have here is a log p. So if you remember from calculus, this is a lot easier if we just say that this is logs are base e. So I'm just going to write this is a natural log. And so the reason we want to do this is just because if we used a different type of log, we would have an extra kind of constant term to correct for that. When we take a log, if we do a natural log, it works out very nicely. We get 1 over p. Okay, then we have this term here. Okay, so this is, with respect to p, we're going to get the log part turns into 1 over 1 minus p. But remember, the chain rule says we've got kind of this outer part. Now we multiply it by the derivative with this inner part. And so we're going to get an extra negative here. And then, of course, this xi minus 1 is just a constant that gets multiplied. So if you're rusty on your kind of derivative rules, you might want to go back and look over them. But basically, logs turn into 1 over the things of the log. This turned into 1 over the thing inside the log, but we also had to do the chain rule, and we got a -1, and the constant kind of just stayed where it was. Okay, so let's kind of see if we can simplify this a little bit. So this kind of sum goes over the entire thing. Let's move it in. This here does not depend on I. So what we can do is if this I goes from 1 to n, right, I equals 1 to n, well, that means that this first term here is just going to turn into n over p, because we have a sum over n items where each is 1 over p, and so we just multiply by n. So the first term turns into that. Okay, so now let's look at these other terms. Okay, so here we have, actually I'm going to turn this into a minus. Just move this minus sign over. Okay. Now 1 over p, sorry, 1 over 1 minus p also doesn't depend on n. And then we're going to have here, if we move the sum in, this turns into sum I of xi. And this is going to be, we're just doing a bunch of 1s. So n times 1 is just n, and that'll be a minus n, right? Okay. So all I did here is just simplifying what we got from the derivative, and we ended up with this. Okay. So now this is the derivative. It's a little bit simplified. What do we want to do? Well, we want to find the max. We're going to set it equal to 0. And in particular, we're going to solve for p. What is the particular value of p that will lead this derivative to be equal to 0? Okay, so what does this end up telling us? Well, that tells us that n over p is equal to 1 over 1 minus p times the sum of the xi's minus n. All right? And now we're just going to need to solve for p. So let's move this over here. We have n times 1 minus p over p equals the sum over xi minus n. And remember, of course, this n is outside the sum. Okay, so now we have n over p, and we have minus, this is p times n over p. Well, that's just going to be n equals the sum of xi. Is this part right? We're going to just copy over. Okay, now we can add n to both sides. And now I'm going to move the p up and the sum of x's down. And what does that tell us? P is going to be equal to, let's see, n over the sum of xi. Okay, so now what we've ended up with is we have a general rule for how to get a p given a set of points. So if we have some set of points, we're going to take the sum down at the bottom, and then we're going to take the number of them n at the top. And this will give us the maximum likelihood choice of p. So now that I've done this whole derivation here, in the end what we want is for our particular set of points given here. And so I'm just going to fill these in. Well, what do I need to know? First I need to know the sum. So what is the sum of all these points? So we take the 7 and the 3, 5 and 5, and an 8. Well, that's going to be 28. And what's the number of points? Well, there's just 5 of them. So our final answer here is 5, the number of points, divided by the sum of the points, which is 28. So what we can see here is, now that we've got this general formula, it's very easy to plug in for any arbitrary set of points and find what is the maximum likelihood choice of p. And that's it for problem number 3 and for this section. Thanks.